We will now look at pneumatic systems. Pneumatic referring to a compressed gas. Pneumatic systems use air pressure to create mechanical motion. As shown, the basic systems include an air intake filter that traps dirt before it enters the system, an air compressor that provides a source of compressed air, a dryer that removes moisture in the air, a pressure tank that is a reservoir of compressed air, a pressure regulator that maintains air pressure, a valve that controls air flow, and a pneumatic cylinder that creates the mechanical motion. Pneumatic systems are very similar to hydraulic systems, but there are several important differences. The major functional difference is that air is compressible, whereas hydraulic fluid is not. In fact, air is so compressible that the air in the average car tire would occupy 3 times its volume at atmospheric pressure. To explore this concept further, consider a bicycle pump being used to inflate a tire. When you push down on the plunger, the air in the pump is compressed until the air pressure in the pump is greater than the pressure in the tire, at which point some portion of the air flows out of the pump through a one-way check valve into the tire. If you were to push the plunger down only halfway and let go, the compressed air in the pump cylinder would expand and push the plunger partway back out. If for some strange reason you were pumping an incompressible fluid, such as water, into your tire, you would notice a big difference. Pushing the plunger halfway down would not compress the water volume, so exactly half the water in the cylinder would be expelled into the tire. And if you were to let go of the plunger in mid-stroke, the plunger would not rebound because water under pressure does not expand. The point of this analogy is that a pneumatic system tends to be springy, whereas a hydraulic system is rock solid. The position of a hydraulic cylinder is strictly a function of the volume of fluid in the cylinder, whereas the position of a pneumatic cylinder is a function of the air pressure, which in turn depends on the resistance of the mechanical load and the temperature. For example, if a hydraulic actuator is moved to position and stopped, the trapped fluid on each side of the piston will lock it in place. If a pneumatic actuator is moved into position and stopped, the piston can be displaced by pushing or pulling on it with enough force. The trapped air in the cylinder simply compresses somewhat. For this reason, pneumatic systems are not usually used when accurate feedback positioning is required. Instead, positioning is achieved by having the piston travel back and forth between 2 mechanical stops, and enough air pressure is provided to guarantee that the piston can move any expected load. Another difference between hydraulic and pneumatic systems is that pneumatic systems do not have to return the low pressure air to a compressor. They simply exhaust it to the atmosphere, clearly an advantage. Another advantage is that pneumatic systems are not messy. Hydraulic systems can and do leak. Pneumatic systems also leak, but there is no spills to clean up. Also, pneumatic systems tend to be smaller and less expensive. All these qualities make them very attractive as a source of mechanical motion in cleaner, high-tech industrial environments. A control system that uses pneumatic actuators would include a controller along with the pneumatic components. The controller specifies when the individual valves in the system are to be turned on and off. Usually, the controller is a digital electronic device, such as a microcomputer or a programmable logic controller, or PLC. However, some controllers are strictly pneumatic devices and use no electronics at all. Pneumatic controllers make use of pneumatic logic devices, actual and or NOT gates that operate only on air pressure. The output signals from these controllers are of course pneumatic and are conveyed to the control valves through small tubes. Although pneumatic controllers are still used extensively in some applications, such as simple sequencers and around flammable gases, in general, industry is backing away from this concept. The air compressor is a machine that pumps air from the atmosphere into a tank. There are a number of types of compressors, but one of the most common is the reciprocating piston compressor shown. The compressor crankshaft is driven by an external power source, typically an electric or diesel motor. As the crankshaft rotates, the piston is forced up and down in the cylinder. The air is drawn into the cylinder through a valve during the intake stroke, figure A, and then during the exhaust stroke, figure B, the air is pushed out through another valve into the pressure tank. Water vapor in the compressed air must be removed, or it will eventually damage the pneumatic components. Removing the moisture in the air is done by the dryer, of which there are several types. One type, an aftercooler, chills the air, causing the moisture to condense into drops, which can then be drained off. The desiccant dryer circulates the air through a moisture-absorbing chemical called desiccant. When the desiccant becomes saturated, often indicated by changing color, it must be changed. The receiver tank, or the pressure tank, receives air from the compressor and becomes the high-pressure air reservoir of the system. Power to the compressor motor is controlled by a pressure switch on the tank. When the tank pressure falls below a set value, the switch closes and the compressor motor starts. When the tank pressure increases to a specified value, the switch opens, turning off the compressor. One benefit of using the tank is that it tends to smooth out the pulsations of the air pressure that result from a reciprocating piston compressor. The typical pressure range of a pneumatic system is 30 to 150 psi, which is 200 to 1000 kPa, although some systems go as high as 750 psi or 5000 kPa. Pressure regulators. The tank pressure can range anywhere between the high and low limits of the pressure switch. Some systems cannot tolerate this variation and hence require a pressure regulator to be installed between the tank and the system components. The pressure regulator can supply air at a constant pressure regardless of the source pressure, as long as the source pressure stays above the desired regulated pressure. A spring-loaded diaphragm is pushed on by regulated air pressure. If the regulated air pressure starts to fall, the reduced pressure of the diaphragm causes it to move downwards, thus opening a valve and allowing more high pressure in. Pneumatic control valves. Pneumatic control valves regulate the airflow, which in most cases means on or off. Many configurations are possible, but of particular interest is the bidirectional control valve that causes a piston to move in either direction. A pneumatic bidirectional control valve is shown. It is functionally similar to the hydraulic control valve, but there are some differences. For instance, pneumatic control valves use O-rings, rubber seals, to minimize internal leaks. Pneumatic valves are usually designed to be full on or completely off and are driven by either an electric solenoid or a pneumatic control signal. Finally, these valves require only one tube coming from the air supply. The used air from the cylinder is simply vented to the atmosphere. Pneumatic actuators convert air pressure into mechanical motion. There are two basic types: linear actuators, cylinder, piston or diaphragm types, and rotary actuators. Pistons and rotary actuators are functionally similar to their hydraulic counterparts. Pneumatic cylinders are available in a variety of shapes and sizes. There are two basic internal configurations. The double acting cylinder connects to the valve with two tubes and can be driven in either direction. The single acting cylinder can only be driven in one direction with air pressure and is returned by a spring. Let's look at an example. A spring-loaded single-acting cylinder has a diameter of 2 inches and a stroke of 2 inches. The return spring has a spring constant of 3 pounds per inch. The available air pressure is 30 pounds per square inch. What force can the cylinder supply to a load at the end of the stroke? The solution: the total force that the piston can supply can be calculated from equation 10.1 in exactly the same manner as it was done for the hydraulic cylinder. First, we calculate the piston surface area to be 3.14 square inches. Now find the force from the equation 10.1. F is equal to PA, which comes out at 94.2 pounds. However, some of this force is used to compress the spring and is not available to the external load. The force needed to compress the spring 2 inches is calculated as follows. F is equal to the spring constant times the length, or 3 pounds per inch times 2 inches, is equal to 6 pounds. Therefore, the total available force from the cylinder is the piston force less the spring force, or 88 pounds. Rotary actuators convert air pressure into rotary mechanical motion. One common design is the vane motor. The motor consists of a rotor that is offset in a housing. Protruding from the rotor are spring-loaded vanes that seal against the housing and slide in and out of the rotor as it turns. Motion is achieved because the vanes on the top have more exposed surface area than those on the bottom, and hence receive more force, causing the rotor to turn clockwise.